Nestle Sweetened Condensed Milk, at the heart of all desserts.
Thick, golden, and impossibly sweet. Condensed milk is one of those rare ingredients that somehow turns everything it touches into pure comfort. From Vietnamese iced coffee to tres leches cake, to classic fudge, and even emergency survival rations, condensed milk is everywhere. But have you ever stopped to think about how this sugary milk magic is actually made? Here's a clue. It involves enormous steel tanks, vacuum chambers that suck out water under extreme pressure, and a surprising scientific twist that makes this product nearly immortal on your shelf. Without any preservatives. Sounds simple? It's not. Today, join FactoryX as we take you inside the hidden world of condensed milk production, following every step of the process, from the raw milk at dawn on dairy farms to the tightly sealed cans rolling off high-speed assembly lines by the thousands. And it's not just a mechanical process. It's a story of chemistry, microbiology, food safety, and surprisingly, global economics. Let's be clear. Condensed milk isn't just evaporated milk with sugar thrown in. It's a completely re-engineered product that requires precision to ensure the milk doesn't curdle, separate, or ferment. Factories have to strike a perfect balance of fat content, temperature, pressure, and timing. One slip, and the whole batch is ruined. But when everything goes right, what you get is a stable, thick, and ultra-sweet product with a shelf life of up to 2 years. A modern miracle of food engineering that stood the test of time for over 150 years. Before we get into the factory machinery and step-by-step process, we need to set the stage. Because the story of condensed milk is much bigger than just the assembly line. It's about necessity, innovation, and how human ingenuity turned something as perishable as fresh milk into a food that could travel across oceans, survive desert heat, and still taste like dessert. Let's rewind the clock to the early 1800s. At the time, milk was a dangerous product. There was no refrigeration, no pasteurization. If you lived in a city, by the time milk got to your kitchen from a distant farm, it was often already contaminated. People were dying from spoiled milk, especially children. Infant mortality rates were staggeringly high, and milk was one of the culprits. Enter Gail Borden, a newspaper publisher turned food innovator, who witnessed children dying aboard a transatlantic voyage because of spoiled milk. He became obsessed with finding a way to preserve milk safely. His solution? Evaporate the water and add sugar. Why sugar? Because sugar isn't just for taste. It's a preservative. When you add it to milk in the right ratio, it binds up the water molecules that bacteria need to survive. And when you combine that with boiling off about 60% of the liquid, you've got a product that's thick, shelf-stable, and packed with energy. Borden patented the process in 1856. At first, no one took him seriously. But when the Civil War broke out in the US, the Union Army saw condensed milk as a breakthrough. They needed a way to give soldiers calories, nutrients, and safe dairy without refrigeration. Suddenly, Borden's invention became a military staple. By the time the war ended, condensed milk was a household product, and it quickly spread around the world. In Europe, Asia, and Latin America, it became a pantry essential, especially in places where refrigeration was scarce. Over time, it moved from being purely functional to deeply cultural. In Thailand, it sweetens Thai tea. In Brazil, it's in brigadeiros. In the Philippines, it's the magic in leche flan. And it's still growing. Today, the global condensed milk market is worth billions of dollars, with major production hubs across the US, Netherlands, India, and Southeast Asia. Demand is still rising in developing countries, where condensed milk is not just a treat, it's a nutritional supplement. But here's what most people don't realize. To make condensed milk on an industrial scale requires an orchestra of high-tech processes and food science precision. We're talking multiple stages of filtration, pasteurization, controlled evaporation under vacuum pressure, sugar crystallization control, homogenization, and sterile packaging. All happening at lightning speed. One 24-hour shift at a medium-sized dairy plant can process over 300,000 liters of raw milk into condensed milk. That's the equivalent of emptying a full-size backyard swimming pool and boiling it down to just the thick, syrupy concentrate every single day. What's more impressive? That all of this happens without the product ever being exposed to open air, ensuring safety, consistency, and zero contamination. If you're imagining giant vats of milk just boiling away on a burner, think again. Modern condensed milk production is more like a chemistry lab than a kitchen. And over the next few sections, we're taking you step by step into this process, from the moment raw milk arrives at the factory gates, to the second it's sealed into a can and shipped across the globe. Along the way, we'll explore the precise fat-to-solids ratio that makes condensed milk smooth, why vacuum pressure is key to preventing scorching, how homogenizers prevent separation even after months on a shelf, and why sugar isn't added at the beginning, but at just the right time during evaporation. So, if you've ever enjoyed a spoonful straight from the can or drizzled it over shaved ice, fruit, or cake, you're going to want to stick around. Because what's behind that flavor isn't just milk and sugar. It's science, history, and some truly mind-blowing engineering. Every drop of condensed milk begins its life on a farm just after dawn. Cows are milked in automated milking stations, many of them equipped with sensors and smart tech to monitor everything from cow health to yield consistency. But that's only the beginning. The journey from cow to can involves an astonishing number of steps, starting with one of the most critical: collection and clarification. Once milk is harvested, it's chilled to around 4 degrees immediately. Why? Because milk spoils fast. At room temperature, bacteria begin multiplying almost instantly. To prevent this, dairy farms use bulk cooling tanks to store the milk in cold, sterile conditions until it's picked up, usually within a matter of hours. Tanker trucks, made from stainless steel and heavily insulated, arrive at the farms daily. These trucks are more than just transportation. They're mobile refrigeration units. The milk is kept cold during the entire journey to the processing facility, sometimes covering hundreds of miles, depending on the country. And before a single drop enters the factory, it undergoes a critical checkpoint: initial quality inspection. This is where things get serious. At the factory gate, technicians run tests on the arriving milk to ensure it meets strict criteria. They're checking for temperature. If the milk isn't still cold, it's rejected. Smell and color. Any off odors or discoloration could mean spoilage. Fat and solids content. This determines whether the milk is rich enough for condensed milk production. Bacterial load. High microbial counts can contaminate entire batches, so strict thresholds are enforced. Sometimes, rapid microbiological tests are performed using specialized kits that give results in under an hour. If a load fails even one test, it's rejected immediately. Once accepted, the milk enters the clarification and separation stage. Here's where some science kicks in. In this phase, the milk is pumped through a centrifugal clarifier, a high-speed spinning system that separates out impurities, sediment, and even somatic cells, basically dead cells from the udder. Think of it as a high-tech filter that uses centrifugal force rather than mesh. At the same time, some factories also use centrifugal separators to partially remove or adjust the cream content of the milk. This is known as standardization, and it's crucial to condensed milk production. Why? Because condensed milk needs a very specific fat-to-solids ratio to achieve the right thickness, sweetness balance, and stability. If it's too fatty, it will separate during storage. If it's too lean, it won't taste rich enough, and the texture will be watery. To maintain consistency, the factory blends milk from different sources, sometimes even from multiple farms or regions, to hit an exact target. In many plants, the ideal fat content is around 8% after standardization. That's higher than regular drinking milk, but lower than heavy cream. Once the milk is clarified and adjusted for fat, it's time for preheating. This is done in large plate-type or tubular heat exchangers. The milk is gradually heated to around 85 degrees Celsius for a short duration. This process serves several purposes. Kills pathogenic bacteria, acting as a pre-pasteurization step to make the milk safe. Deactivates enzymes like lipase and protease, which could spoil flavor or texture later. Prevents curdling by stabilizing milk proteins ahead of evaporation. It's important to note this isn't a full pasteurization like in milk cartons. It's a controlled heat treatment that readies the milk for concentration without damaging flavor. And here's a surprising twist. Some factories actually add a small amount of stabilizer at this stage, usually something like sodium bicarbonate or phosphate. This isn't to change the flavor. It's to improve the milk's ability to withstand the intense heat and pressure of the next phase, evaporation. But before we move on, here's a detail that's often overlooked: timing. From the moment milk leaves the cow to the point it's heated in the plant, factories aim to keep that window as short as possible. In top-tier plants, it's less than 12 hours. This rapid processing is key to preserving not only the safety, but also the taste and nutritional value of the final product. And this brings us to the final step of pre-processing: holding tanks. Once standardized and preheated, the milk is pumped into large stainless steel storage tanks called balance tanks, which feed the evaporators on a continuous basis. These tanks are heavily insulated and constantly agitated to prevent settling and maintain uniformity.
Fun fact, these tanks can hold tens of thousands of liters of milk at a time, and some plants operate on a 24/7 schedule, with fresh milk coming in daily and condensed milk going out in round-the-clock cycles. This system allows for massive volumes to be processed without compromising quality. To summarize this phase, milk is collected chilled and quickly transported in sterile tankers. At the plant, it's clarified, standardized for fat, and preheated. It's held temporarily in sterile tanks, ready for evaporation. And all of this, it happens before a single molecule of water has even been removed. The real transformation, where thin milk turns into thick syrup, is coming up next. And it requires an engineering marvel: the vacuum evaporator. Get ready, because in the next section, we'll explore how factories remove over 60% of milk's water content without burning it, and why pressure, temperature, and timing have to be controlled down to the decimal. Once the milk is clarified, preheated, and stabilized, it's ready for the most dramatic step in its transformation: evaporation. Now here's the challenge. Milk is over 85% water. To create condensed milk, factories must remove around 60% of that water, without burning the milk, curdling the proteins, or compromising the flavor. And they must do it fast, efficiently, and without exposing the milk to open air. So how do they pull that off? The answer lies in one of the most powerful and elegant machines in food processing: the vacuum evaporator. The problem with boiling. Let's start with the obvious question. Why not just boil the milk? Simple. You can't. Boiling milk at atmospheric pressure would scorch it. It would create a burned flavor, destabilize the proteins, and cause it to foam, bubble over, or curdle. Not to mention, boiling large volumes of milk in open kettles would waste time, energy, and risk contamination. That's where vacuum evaporation comes in. By reducing the pressure inside a sealed chamber, you also lower the boiling point of water. Under partial vacuum, water can boil at around 45 to 65 degrees Celsius, far gentler on milk than traditional boiling. This allows factories to concentrate the milk without damaging it, preserving flavor, color, and texture while still removing massive amounts of water quickly and efficiently.
Multi-effect vacuum evaporators. Most modern condensed milk plants use multi-effect falling film evaporators. That might sound like science fiction, but here's how they work in simple terms. Milk enters the evaporator as a thin film along the walls of vertical steel tubes. Heat is applied gently through steam jackets on the outside. Inside the tubes, water begins to evaporate, but under vacuum, this happens at lower temperatures. As steam, water vapor, rises, it's pulled out and condensed separately. The partially concentrated milk flows downward and is collected. But that's just one effect. In multi-effect systems, the steam generated in the first chamber is reused to heat the next stage, and then the next, sometimes up to 5 stages in a row. This multiplies the efficiency of the system and slashes energy costs dramatically. It's a beautiful example of industrial recycling, using steam to make more steam, all while protecting the milk and removing water. Targeting the right concentration. Throughout the process, the milk's solids content, especially sugar, protein, and fat, is constantly monitored. Sensors measure Brix, which is the percentage of dissolved solids in the liquid. For sweetened condensed milk, the goal is typically around 60 to 65% total solids by the end of evaporation. Remember, at this stage, sugar still hasn't been added. The milk is being concentrated into what's essentially a very thick evaporated milk base. It's creamy, rich, and very viscous, but still bland compared to the final product. Depending on the plant and batch size, this evaporation step can take as little as 15-20 minutes, thanks to the vacuum and heat exchange system working in perfect tandem. Process control and monitoring. Now, imagine this whole setup running non-stop, 24 hours a day. That's where automation comes in. Modern evaporators are tightly controlled by PLC systems, programmable logic controllers, that monitor vacuum pressure in each stage, flow rates of milk in and concentrate out, temperature gradients, final solids concentration. If any one of these variables goes off target, the system self-adjusts or alerts operators. Even the tiniest error, a drop in pressure or a spike in temperature, can ruin thousands of liters of product. Some factories even use inline infrared sensors that take constant readings without touching the product, keeping things sterile and ultra-efficient.
Quest: why sugar isn't added yet. Here's a detail most people don't expect. Sugar isn't added before evaporation. It's added after. Why? Because sugar thickens the liquid and dramatically raises its boiling point. If you tried to evaporate milk with sugar already in it, you'd need more heat, more time, and you'd risk scorching the product. Plus, the sugar itself could begin to caramelize too early, leading to an off-color or burnt taste. By concentrating the milk first, then adding sugar, factories keep the process smooth, stable, and perfectly timed. But don't worry, we'll get to that sugar step in the next section. For now, we're at the moment when concentrated milk, thick, steamy, and warm, is ready for its sweetest transformation. At this point, the milk has gone from a watery, thin liquid to a thick, rich concentrate. It's not quite condensed milk yet, but it's close. Next comes the sugar, and with it, a whole new level of complexity. Because adding sugar isn't as simple as dumping it in. It affects the product's chemistry, preservation, and shelf stability, and factories have to do it with military precision. In the next section, we'll cover why sugar makes condensed milk shelf-stable, how factories control crystallization and texture, and why this stage determines whether the final product is smooth or gritty. Sugar, addition, shelf stability, and crystallization control. Up until now, everything we've seen has been about preparing milk for concentration. The heat, the vacuum, the separators, they've all worked in perfect sync to remove water and stabilize proteins. But here's where the process truly earns its name. Because what separates evaporated milk from condensed milk isn't just the thickness, it's the sugar. And this next step, it's where both preservation and flavor are locked into place. The role of sugar in condensed milk. First, let's break a myth. Sugar isn't just added to make condensed milk sweet. It's added to make it safe. Here's how. When you dissolve sugar into the concentrated milk at a high enough percentage, typically 40 to 45% of the final weight, it lowers what scientists call the water activity, or awe. That's the measure of how much free water is available for microorganisms to grow. Without enough free water, bacteria can't survive. Yeast can't ferment. Mold can't bloom. That's why properly made condensed milk can last for up to 2 years without refrigeration, even after the can is opened. Sugar binds with water molecules and essentially locks them out of biological activity. In other words, sugar doesn't just sweeten condensed milk, it preserves. But here's the tricky part. This isn't just table sugar sprinkled in like a cup of flour. In industrial plants, the sugar addition stage is a tightly engineered operation involving precise timing, ratios, temperatures, and mixing speeds. Sugar ratios and dosing factories typically use refined sucrose, white cane or beet sugar, which is dissolved into either a concentrated syrup or directly mixed into the evaporated milk. For most standard condensed milk recipes, sugar makes up about 44 to 46% of the final product by weight. The milk solids, proteins, lactose, fat, make up around 28 to 30%. The remaining 25 to 28% is water that remains after evaporation. This gives sweetened condensed milk its thick, rich viscosity and intense sweetness. The sugar syrup is either made on site or pre-delivered, and it must be preheated to match the temperature of the milk concentrate, typically around 60 to 70 degrees Celsius, 140 to 158 degrees Fahrenheit. If it's too hot or too cold, it could cause localized crystallization or separation. Then comes the actual blending, high-speed mixing and homogeneity. In many factories, the concentrated milk and sugar syrup are mixed in high-shear blending tanks, large stainless steel vessels equipped with impellers or rotor stator systems that spin at thousands of RPM. Why the high speed? Because sugar is a crystal by nature. If not mixed fast enough, it starts to reform into solid crystals once it cools, creating a gritty, sandy texture in the final product. To prevent this, the mixture must be uniformly heated, thoroughly agitated, maintained at stable temperature and pH. Some plants also use vacuum blending tanks, which pull excess air out of the mixture to prevent foaming and ensure the final product remains glossy and dense. Once the sugar is fully integrated, the product officially becomes sweetened condensed milk. But we're not done yet, because sugar introduces a new challenge: crystallization control. Controlling crystallization. Even though sugar keeps milk shelf-stable, it can cause a major problem during cooling: crystallization. If left unchecked, large sugar crystals will form as the product cools. This doesn't affect safety, but it ruins the texture. The milk becomes grainy, less creamy, and harder to pour or spread. To prevent this, factories must carefully seed and control the crystallization process. Here's how it's done. Cooling the mixture slowly to just below the saturation point, adding fine seed crystals of lactose or sucrose. These microscopic particles encourage even crystallization on a nanoscale, preventing large, gritty chunks from forming. Constant agitation during cooling to keep the mix homogeneous. Timing the cooling so that crystals form at just the right size, not too large, not too fine. This step, though invisible to the consumer, is one of the most important in ensuring that condensed milk remains smooth and spoonable for months. It's also why factory-made condensed milk has a far superior texture to DIY versions. Most homemade recipes don't control crystallization and often result in gritty or overly thick product after a few days. Temperature and texture control. After blending and seeding, the sweetened condensed milk is gradually cooled to around 30 to 35 degrees Celsius, 86 to 95 degrees Fahrenheit, in a process that can take up to an hour, depending on batch size. This cooling phase is monitored in real time using sensors that measure viscosity, thickness, refractive index to determine sugar concentration, pH to maintain protein stability. If any of these drift out of range, operators can adjust flow rates, add seed crystals, or tweak temperatures on the fly to keep the product within spec. By the time cooling is complete, the milk has reached its final texture: thick, smooth, glossy, and uniform. Now it's ready to be packaged. But before that happens, one last step ensures it's shelf-ready: homogenization and final filtration. And believe it or not, all of this happens in under 2 hours, per batch. With multiple batches running concurrently across massive tanks, factories can pump out hundreds of tons of condensed milk per day. In the next section, we'll move on to the final critical stages: homogenization, sterilization, packaging, and storage. Because even the perfect batch of condensed milk can be ruined in the final minutes if the factory doesn't maintain sterility and airtight sealing. And yes, there's even a science behind the way the milk flows into the can. So far, we've watched raw milk transform into something rich, sweet, and shelf-stable. But there's one final layer of precision that makes condensed milk smooth, glossy, and uniform: homogenization. Without it, your condensed milk might separate into layers or develop an odd mouthfeel over time. And when you're mass-producing for global markets, that's not an option. Homogenization, the secret to consistency. Homogenization is the process of breaking down fat globules in the milk so they're evenly distributed and suspended within the liquid. This prevents cream from rising to the top or fat pockets forming over time, especially important for long shelf-life products. In condensed milk production, homogenization usually occurs after sugar addition and cooling, but before packaging. The product is pumped through a high-pressure homogenizer, which forces the mixture through a narrow valve at 2,000 to 3,000 psi. This pressure shear reduces fat globules to microscopic sizes, often below 1 micron. The result? A condensed milk that doesn't separate in the can, pours evenly with consistent thickness, looks glossy and creamy on the spoon, maintains texture for up to 2 years in storage. Fun fact: some factories run the milk through a 2-stage homogenizer, further stabilizing the emulsion and preventing protein clumping during storage, especially in tropical climates where condensed milk is most popular. Sterile packaging and aseptic conditions. Once homogenized, the condensed milk is immediately transferred to the packaging area through fully enclosed stainless steel pipelines. This part of the process operates under aseptic, sterile conditions, meaning zero exposure to open air, dust, or microbes. Packaging is done using high-speed filling machines that,
dispense precise volumes of milk into sterilized cans or squeeze tubes. Vacuum seal the containers to remove any residual oxygen. Crimp and seal the lids using heat or mechanical pressure. Stamp the batch number, date code, and expiry directly on the lid or side. Most plants package in 397 grams or 1 kilogram metal cans, though regional packaging varies. In some countries, plastic pouches or tubes are more common for affordability and portability. The entire packaging process, filling, sealing, coating, happens in a matter of seconds per unit. Modern plants can fill up to 200 cans per minute per machine, with multiple lines running in parallel. Final quality control. Before cans are boxed and shipped, they undergo one final checkpoint: quality control inspection. This includes visual checks for dents, leaks, or labeling errors. Weighing to ensure fill volume is exact. X-ray or thermal scanners to detect internal contaminants or seal defects. Random taste and texture testing by lab technicians. Only after passing all these checks does the product move to storage and distribution. Cans are palletized, shrink-wrapped, and stored in temperature-controlled warehouses, awaiting shipment to supermarkets, bakeries, and food distributors around the world. And there you have it. Milk that was collected just 24 to 36 hours ago is now a sealed, sterilized product that can last 2 years on a shelf, ready to be shipped across oceans and deserts without refrigeration. From the cow to the can, every second of this process is engineered for one thing: safe, consistent sweetness that never spoils. Condensed milk isn't just a product, it's a global phenomenon. From street stalls in Southeast Asia to bakeries in Latin America, it's become an essential part of daily life. And the reason why? It goes beyond sweetness. It's about access, affordability, and reliability, especially in regions where refrigeration and fresh dairy are inconsistent or unavailable. Let's zoom out for a second. Today, the global condensed milk market is valued at well over $8 billion and growing steadily year after year. Major production hubs include the US, India, Germany, Brazil, and Thailand, each exporting to dozens of countries across Africa, Asia, and the Middle East. Why the growing demand? Because condensed milk hits a perfect economic sweet spot. It's shelf-stable for years, high in calories and nutrients, affordable to produce and distribute, versatile across cuisines. In many developing nations, condensed milk serves as both a dessert ingredient and a nutritional supplement. It's often used to replace fresh milk in tea, coffee, porridge, and even baby food in emergencies. The added sugar makes it high energy, ideal for regions facing food insecurity. But what's most remarkable is how condensed milk has been adopted and adapted into local food cultures around the world. Cultural favorites around the globe. Vietnam. Sweetened condensed milk is a staple in café sua da, Vietnamese iced coffee brewed with dark roast beans and poured over condensed milk. Brazil. Used in brigadeiros, a beloved chocolate truffle made with just 3 ingredients: condensed milk, cocoa, and butter. Philippines. The heart of leche flan, a creamy caramel custard served at every major holiday. India. Mixed into sweets like barfi and kalakand, or simply spread on toast. Thailand. Drizzled over roti, mango sticky rice, or served with shaved ice desserts. In each of these countries, condensed milk is more than just an ingredient. It's nostalgia in a can, tied to tradition, celebration, and comfort. And let's not forget how condensed milk revolutionized global food trade. Because it's light, compact, and long-lasting, it became a wartime staple, a humanitarian aid essential, and a critical product during natural disasters and supply chain breakdowns. Even today, it's found in military rations, refugee food packs, and emergency response kits, proof that its original role as a survival food hasn't disappeared. From luxury desserts to basic nutrition, condensed milk has evolved into a food that sits at the intersection of culture, science, and economics. It bridges the gap between rural farms and urban megacities, between poverty and celebration, and between tradition and innovation. And behind every can is a story of engineering, preservation, and global connection, all from a simple blend of milk and sugar.
So, the next time you crack open a can of condensed milk, whether you're making a cheesecake, drizzling it into your coffee, or just sneaking a spoonful straight from the tin, you'll know there's a lot more behind it than just milk and sugar. You've seen the full journey, from early morning dairy collections on rural farms, to vacuum evaporation systems removing water without a trace, to sugar integration, crystallization control,
high-pressure homogenization, and sterile packaging, all operating with the precision of a pharmaceutical lab. What looks like a simple can is actually the product of over 150 years of food science innovation, driven by necessity, perfected by engineering, and embraced by cultures across the globe. Condensed milk represents one of the rare food products that successfully bridges gaps between luxury and survival, between ancient traditions and high-tech factories, between sweetness and sustenance. And it continues to evolve today, with new flavors, formats, and functional uses showing up in everything from ready-to-drink beverages to vegan dessert alternatives. But perhaps what's most surprising is this. In an age of processed foods, preservatives, and artificial additives, condensed milk remains incredibly simple. Just 2 ingredients: milk, sugar, that's it. The rest is knowledge, timing, and technology working in perfect harmony. If this deep dive made you appreciate what goes into every can of condensed milk, do us a favor. Hit that like button, subscribe, and leave a comment below with your favorite condensed milk recipe or memory. Whether it's Thai iced tea, Brazilian brigadeiros, or that one dessert your grandmother used to make, food is memory, and we'd love to hear yours. And if you enjoy exploring how everyday things are made, especially when there's a story behind the science, make sure to turn on notifications. We've got more fascinating factory breakdowns coming your way, from chocolate bars to instant noodles, ice cream to industrial baking. Because behind every bite you take, there's a process worth watching. Thanks for watching FactoryX, where we take you inside the world behind what's on your plate. Until next time.